Okay, so today we have Andrea Ferragutti, and he will be talking about Frobenius and settled elements in iterated Galois extensions. Thank you, Andrea.
Thank you for the invitation. I'm very happy to speak at your seminar and present this last work of ours. So this project I've been working with Carlo Pagano, which is in Montreal. So let me start from the very basic motivation for this work, which is sort of a very natural, naive question. So start with a field K and take a polynomial with coefficients in K of degree at least 2 to make the question non-trivial. And as customary in arithmetic dynamics, we denote by Fn, this way not the power of the polynomial f, but the nth iterate, so the composition of f with itself n times. And the question we ask is, how does the factorization of these iterates vary when n gets larger and larger? And so one first thing that can happen is that, for example, all these iterates are irreducible. And when this happens, we say that f is stable or dynamically irreducible, which is sort of a better thought definition, like word-wise, but I like the old one, so I'm gonna call it stability and not dynamically irreducibility, but you can find both in the literature. So you say that f is stable when all the iterates are irreducible. Right, so this is sort of the easiest possible behavior in a way. And surely you can find examples, and it's even easy to find them because, for example, Eisenstein polynomials are stable. And so Eisenstein polynomial, now I didn't write down the definition again, but it just means that there is some prime that divides all. So let's say f is monic, there is some prime that divides all the coefficients, but the square of that prime does not divide the constant term of the polynomial. So that's an Eisenstein polynomial. And it's a very easy induction exercise to see that the iterates of Eisenstein polynomials are Eisenstein. And it's a very well-known fact that Eisenstein polynomials are irreducible. And therefore, putting together these two basic facts, you see that Eisenstein polynomials are stable. But surely there are more examples than this. And so let me introduce this definition that is going to play a crucial role later on in the talk. So suppose you have a quadratic polynomial, x squared plus c for simplicity. You can always reduce to this form, getting rid of the linear term for what I will say in this talk. But just for simplicity, just take x squared plus c. So what we call the adjusted postcritical orbit of f is the sequence that is defined recursively in the following way. So the first term is just minus c, and then the other terms are just the orbit of 0, right? So Cn is just the image of 0 via the nth iterate of the polynomial. So this is just the orbit of 0, but the first term has the opposite sign. And now it's a theorem. I didn't attribute to anyone, but I guess it should be possible to track it down, probably to Odon in the 80s, that if this adjusted postcritical orbit contains no squares, then the polynomial is stable. And for example, take a very simple non-Eisenstein polynomial, which is x squared plus 1. So here there is no prime that divides all the coefficients. And this is a stable polynomial. It's very easy to see, right? Because when you iterate in 0, you always get a square plus 1. And it's easy to see that since the orbit is made of integers, no element in the postcritical orbit is going to become a square, because as soon as elements of the orbit become large, when you square them and add 1, you're not going to find another square. And you also see why it's important to swap the first sign, right? Because so irreducibility of x squared plus c, so the first iterate, is given by the quadraticity of minus c, not c. So this is the reason why the first element has the opposite sign. So this is an example of a stable polynomial, which is not Eisenstein. Now let's push the question a little bit further. Okay, so stability is an example. What is another type of behavior that can happen? And so for this, I need further definition, which is just a slight generalization of stability. So we say that a polynomial g is f stable if when you compose g with all the iterates of n of f, you end up with an irreducible polynomial for every n. So we say that the polynomial
Excuse me,
is
sorry.
yes, sure.
Did you say K is a number field?
No, K is just any field. For now,
Any
it's
field.
any field. Yeah, yeah. Then I will specialize to number fields.
Okay.
Yeah, but for now, just any field. These definitions, they make sense in general. So we say that a polynomial is eventually stable if some iterates, there exists an iterate, which is a product of f-stable factors. And what does this mean concretely? It means that at some point, the factorization of these nth iterate is a model for the factorization of all the subsequent iterates, right? So you will find a certain number of irreducible factors that when you compose them with the iterates of f, they stay irreducible. So in other words, an eventually stable polynomial is a polynomial where the number of irreducible factors of the iterate is eventually constant. This is why the name eventually stable. So if you look at the sequence that gives you the number of irreducible factors of the iterates, this sequence is eventually constant. Are there eventually stable polynomials? For sure. For example, x squared, of course, if a polynomial is stable, in particular, it is eventually stable. But if you pick, for example, x squared, you pick, for example, x squared minus 4, which is reducible, so it cannot be stable. This is eventually stable. So this you can even prove it. And what happens is simply that f splits into two linear factors. But when you keep composing with f, you get two irreducible factors. Okay, so for all the successive iterates of f, the behavior, the factorization behavior is very regular, right? You always have just two irreducible factors of degree 2 to the n minus 1 over q. So, of course, when you make examples, it's important to specify the base field, of course. Right, okay, so this is just a slight generalization, if you want, of the concept of stability. So now let's push the question even further. Are there polynomials that are not even eventually stable? And one can make the following very elementary remark, which is the following. So suppose that you have a polynomial such that 0 is a periodic element for f. So this means that some iterate of 0 is 0. And so what happens is that f to the n of 0 is 0 for infinitely many n, which is the same of saying that the polynomial x divides infinitely many iterates of f. And therefore, of course, f cannot be eventually stable, because in an eventually stable polynomial, the degrees of the irreducible factors, they need to grow. So here we will always have an irreducible factor of degree 1. So a polynomial where 0 is periodic definitely cannot be eventually stable. So this is very, very elementary remark, very easy example. Of course, you can make up examples of polynomials where a 0 is periodic. Are there other examples? Well, according to this conjecture of Jones and Levy, at least for quadratic polynomials over global fields. So here K must be either a number field or function field, the global function field of characteristic not 2, because of course in characteristic 2 then everything goes wild. If 0 is not periodic for f, then f is automatically eventually stable. So according to this conjecture, there are no other examples. So this is the only thing that can go wrong. And in fact, there are some partial results toward this, such as the following theorem of Hadu. For example, when c is such that 1 over c is not an integer, then x squared plus c as a polynomial with coefficients in Q. So here it's very important. In fact, I actually think that it might generalize to some extent to number fields. But at least over Q, this polynomial is eventually stable. And in fact, you can also sort of guess why this is true. because if the number of factors keeps growing and the valuation of C somewhere is positive, then there is going to be a problem because the product of the constant factors of the iterates will need to have the same valuation of C. Because if C has a negative valuation, when you look at iterates of the polynomial f, the valuation of C will be the smaller one, so the winning one. So you cannot have too many irreducible factors. This is sort of the very roughly the idea behind this proof. Okay, so fair enough. Now the question is, what happens over finite fields? Why over finite fields? Well, because if you just look into examples, it looks like the behavior is much different. And there is also a sort of a theoretical reason why one should believe that the behavior is much more chaotic in a way. So, for example, so when I was preparing this talk, I was wondering, okay, do we know of an example of a polynomial over a finite field that is not eventually stable, but where zero is not periodic? And it sort of does not really exist. I asked Vefa Goxel, which is a big expert on this topic, and he also confirmed me that he doesn't know of any single provable example. But nevertheless, if you look into, say, numerical experiments, you realize that there are a lot of polynomials, such as this one in the slide, for example, x squared plus 1 over f7. So this surely, okay, checking that zero is not periodic is very easy. And if you look at the first, I don't know, 20 iterates of f, or as far as the computing power of your computer allows you, you see that the factorization of these iterates is definitely not regular. So this polynomial appears to be not eventually stable. And in fact, so these, in order to sort of explain the behavior of these type of polynomials, Boston and Jones introduced the following notion. So suppose you have an odd prime power and a quadratic polynomial and over a finite field, and call G1 up to GRN the f-stable factors of Fn. And now what you can do is you can sum up the degrees of the f-stable factors of the nth iterate, and you get this quantity Sn. And now you say that f is settled if the limit of, so the proportion of f-stable factors, the weighted proportions, tends to 1. So Sn is, yeah.
And what do you mean by f-stable factors of Fn?
So the f-stable factors are so irreducible factors that have the property of being f-stable. So when you compose them with the iterates of f, they remain irreducible.
And so you always have, but this could be empty or something.
Oh, it can be empty. Yeah. I'm not saying this limit exists. I'm just saying if the limit exists,
okay.
Yeah, if it exists and is equal to 1, then you say that in fact, I don't even know if we can prove that the limit always exists. But anyways, we say that f is settled when this proportion tends to 1. So this is, in a way, the smallest weakening possible of the idea of being eventually stable. Because of course, if f is eventually stable, then from a certain point on, all the factors are f-stable. So this Sn is eventually equal to 2 to the n. So this ratio is exactly 1, eventually. So of course, the limit is 1. So this is a slight weakening of the idea that this ratio is 1. You just ask that the limit of the ratio is 1. And Boston and Jones really conjectured that all quadratic polynomials that are not x squared, because x squared, of course, is very wild with respect to these, are settled. And they have a Markov chain model that conjecturally describes the behavior of the factorization of the iterates. And this model was refined subsequently by Boston, Goxel, and Xia, found out that certain patterns cannot arise, some very complicated stuff. Now, when you have a number field, so let's focus for a moment on the global setting, and you have a polynomial with coefficients in k, and you pick a prime of k that does not divide the determinant, the discriminant of g, then the factorization of g modulo p is described by the orbits of a Frobenius element at p in the Galois group of the polynomial. So this is just very, very classic algebraic number theory graduate stuff. So there must be a way of describing settledness, the property of being settled, in terms of Frobenius elements. How do we do it? So here is where this very nice theory of arboreal Galois representations enter the picture. So this is something that dates back to the 80s, the work of Odoni in the 80s, but this modern language of arboreal Galois representation was just sort of invented by Boston and Jones only in the early 2000s, so some 20 years after. Now I'm gonna focus on a very specific setting, but you can play this game in a much more general setting. But for now, let's focus on this specific setting where k is a field and we have a quadratic polynomial such that all the iterates are separable. So all the roots of all the iterates are distinct. Now, if you look at this set, T infinity of f, which is simply the set of all roots of all the iterates of f, inside an algebraic closure of k. So what is easy and funny to notice is that you can give this set a structure of a graph. So this is an infinite regular binary tree. What does it mean? What do these words mean? So regular means that every node in the tree has exactly 2 descendants, which is regular binary. And I forgot the adjective rooted. So this is a rooted tree. It has a root, which is gonna be 0. So the picture is like the one that you can see. So here I depicted the first 3 levels of the tree. So how does it work? So you have a root, which is just the element 0. Then at distance 1 from the root, you have this element alpha 1, 1 and alpha 2, 1, which are simply the roots of f, which are 2 because f has degree 2. At level 2, so at distance 2 from the root, you have these 4 elements, alpha from alpha 1, 2 to alpha 4, 2, which are the roots of f squared, so f composed with f. At level 3, you have the roots of f3, and so on and so forth. So here there are dots to say that this is in fact an infinite tree. And what do edges represent? So when is a node connected to another node? Simply when f maps one node into its ancestor. Because in fact, if you write it down on a piece of paper, now I cannot write here on the screen, but it's tautologic to see that if you take the set of roots of f to the n, then the map f maps these roots into the roots of f to the n minus 1. So these edges can be seen simply as the action of f. So when you evaluate, for example, this alpha 5, 3, when you evaluate f in this alpha 5, 3, you obtain alpha 3, 2. And when you evaluate f here, you get down to alpha 2, 1. And when you evaluate f in alpha 2, 1, you get 0, because this element is just a root of f. So evaluating f in a root of f just gives you 0. Okay? So connections in this tree just simply mean the action of f. Okay? And of course, you can play this game much more in general. First of all, you don't need to have a polynomial. You can have a rational function. And second of all, the root of the tree can be any element of k. So instead of looking at fx equals 0, we will look at ff equals some fixed element of the field. But I want to avoid being too technical, so I'm sticking to the most simple case. Now, why should this be interesting? So because if you look at the absolute Galois group of your field, so the Galois group of a separable closure of K, so this group acts on the tree via its natural Galois action. And how does it act? Well, simply it permutes the nodes on every level because the Galois group of f to the n permutes the roots of f to the n simply, right? And the roots of f to the n are the elements at level n in the tree. So this is what the action does. But it does something more sophisticated than that, because not only it permutes the nodes on every level, but it preserves the edges. And this is because f has coefficients in k. So if I know that this is harder to explain than to see in a way. But if you act with this Galois group on the tree, what you're doing is you're permuting nodes and you are preserving the relation of being connected by an edge. And therefore, you get an automorphism of this T infinity of f as a graph. You get a graph automorphism. And so you end up with a continuous homomorphism from this big Galois group to the automorphism group of the tree. So continuity here comes out of the fact that these groups, so both the absolute Galois group and the automorphism group of T infinity, they are profinite groups. So they are inverse limits of finite groups. So they have their own natural Krull topology. And this map is continuous with respect to this topology. So this map is what we call the arboreal Galois representation attached to F. Okay? So this is very interesting area of research, very difficult to say things. It's even very difficult, for example, for a given F to compute these representations, to compute their images. There are a whole bunch of conjecture which tell you how large the image of GK should be inside the automorphism group of the tree, and so on and so forth. Now, today, I'm not really interested in discussing any of these. So one thing that you should notice is that, in fact, by Galois theory, the image of this map is simply the inverse limit of the Galois groups of the iterates of the polynomial you started with. So here I put Fn with brackets because it's a mistake, but it should read without these small brackets. And of course, this infinite Galois group is also well defined, even if you take out the hypothesis on the separability of the iterates. So this is just what we call the dynamical Galois group of F nowadays. And of course, this Galois group is the Galois group of the infinite extension of K that you find by adding all the roots of the tree to K. All the roots of all the nodes of the tree, so all the roots of all the iterates of F, you get a very large Galois extension, and its Galois group is exactly isomorphic to the image of this arboreal Galois representation. So from now on, I will denote by omega infinity, just for shortness, the automorphism group of T infinity, okay? So of course, so here I really mean the automorphism group as a graph. So this is why here there is no F. So you should just think of these three as an abstract tree, okay? Abstract, regular, rooted binary tree, which it has its structure of graph. So forget the fact that the nodes are the roots of DFN. Just as an abstract tree, it has its automorphism group, which I call omega infinity, which in fact, it also allows for a very explicit description as an iterated Reith product of cyclic groups over the two. But anyway, so I will call it omega infinity from now on. So let us go back for a second to settled polynomial and settled elements. So since as I was saying before, so factorization of a polynomial modulo P corresponds by classical stuff to orbit decomposition of Frobenius elements when they act on the roots of the polynomials. There must be a notion of settled element inside the automorphism group of the tree, because this should be the Frobenius of the polynomials such that f is settled modulo p. So let me just give this definition for the sake of completeness. So I will denote by Vn the set of roots of Fn, so the set of nodes of T infinity at a distance n from the root. So fix an element sigma in the automorphism group of the tree and fix a node at level n. So we say that V lies in a stable sigma cycle if the following thing happens. So the sigma orbit of V will have some length, a power of 2. This depends on the fact that the group omega infinity is a pro-2 group. So the orbits always have length, power of 2. So this will always happen. So the orbit will always have length, some 2 to the k. And then for every m larger or equal than 1, when you look at the descendant of these nodes at level n plus m, the orbit there is the largest you can hope for. So it has length 2 to the k plus m. This is really the analogous of the analog of thinking that you have an irreducible polynomial, you compose it with some power of f, and you stay irreducible. So you have some orbit of length 2 to the k, you go m levels below that, and you get an orbit which is as big as possible. And how big can it be? Exactly 2 to the k plus m. Okay. So if this happens, yeah, of course.
Sorry, go ahead, finish this.
No, you can.
So when you say length, you mean just the order of the orbit, right? So the number of elements.
The length, by length I mean the cardinality of the orbit, really. Sorry. Yeah. Maybe length is not a precise term. Right. So okay, so now for any given sigma and any given n, we can count how many vertices, how many nodes lie in a stable sigma cycle and call this quantity Sn of sigma. And then we can take the limit over 2 to the n, because of course they can at most be 2 to the n, because the cardinality of the whole set Vn is 2 to the n. And we say that sigma is settled if this limit is 1. So this is exactly the analog of being a settled polynomial. And in fact, as I was recalling earlier, if you have a number field with coefficient and a polynomial with coefficient in k, and you look at the splitting field, well then, the splitting of f modulo p, where p is a prime, say, that does not divide the discriminant of f, well then the factorization of f modulo p is described by the decomposition of a Frobenius in disjoint cycles of the Frobenius acting on the roots of f, right? So f is a product of r irreducible polynomials, each of degree ei, if and only if a Frobenius at p decomposes as a product of r disjoint cycle, each of length degree of gi. Okay, so this is all very classical stuff. And therefore, we immediately get this corollary that simply, if you take a quadratic polynomial x squared plus c, and you take a prime that this does not divide the discriminant, and you look at a Frobenius of a prime that does not divide all these discriminant, then this Frobenius is a settled element exactly when f is settled as a polynomial modulo p. Okay, so this is exactly what gives you the dictionary between being a settled element and being a settled polynomial modulo p. Right. And now, if you go back to the conjecture of Boston and Jones, so they conjecture that any quadratic polynomial over a finite field is settled as long as it's not the polynomial x squared. Well, then their conjecture has this immediate consequence, which is a weaker conjecture, which says that, well, if you have a quadratic polynomial and some good prime, then Frobeniuses of primes that do not divide these discriminants are settled elements. Okay, so this simply rephrasing, if you want, of their conjecture in this setting. So you have to be careful to exclude primes that divides the discriminant. Okay, so their conjecture is more general. This is not equivalent, but it's definitely implied by their conjecture. And so the question is the title of the slide: are Frobeniuses settled? So is it true that Frobenius elements are settled? So I want to make two remarks. The first is that this big Galois group, so this dynamical Galois group, is very different from the Galois group of a number field. So this is a profinite Galois group, it's huge, and it's plenty of elements that are not Frobeniuses, which is not what happens if you take a Galois extension of number field, so a finite extension. Then you have a Chebotarev density theorem, which tells you that every single element is the Frobenius of infinitely many primes. Here, this is very false. Okay, it's plenty of elements that are not Frobeniuses. This can be seen even from a basic counting arguments, because this group is too big. There are only countably many primes, but this group is huge. So there's no way all elements can be Frobenius. So so the situation is more complicated. And the second remark is that this conjecture, if true, is very delicate, because as Oslem nicely proved early this year, if you play the same game and ask the same question, instead of using a polynomial, you use this very simple rational function, and you also have to fix some base point, I think. Then this dynamical Galois group contains no settled elements. So there, definitely Frobenius elements cannot be settled because no element is settled. Okay, it's very, very strong statement. Okay, so and it's a very different situation from that of polynomials. I was quite shocked when I learned of this result, because of course we naturally tend to think that for rational functions everything must work more or less in the same way as for polynomials. This is very false. Okay, so this group contains no settled elements. Right, so after this very, very long introduction, let me get to really the topic of the talk. So the topic is the inverse question. Are settled elements Frobeniuses? This is also
so can I ask a question before you move on to this?
Yes, of course.
Can you give an example of a settled element?
Yeah. I mean, for example, if you take an element that acts transitively at all levels of the tree, that is settled. If you have something that whose orbit such that the orbits are all the nodes at level n for every n, that is a settled element.
But are there examples like this? I mean,
yes,
can I just give my example?
I will tell you an explicit example in 5 minutes. Okay, when I get to describing elements.
Hadi, you can also think of the generators of the monodromy groups at infinity. So those give you settled elements. They're like for for quadratic polynomials at infinity. So you have ramification, and every time the ramification degree. So every time you iterate, ramification degree is 2. So at every level n, you get a order 2 to the n element.
Yes, also.
Those are settled. Sorry.
Okay, yeah, sure. Thank you. So my question is the opposite question. Are settled elements Frobenius? And if I ask the question like this, the answer is of course not. And the reason is just counting. Because, for example, if you take a polynomial whose Galois group is the whole automorphism group of the tree, then again, you have only countably many primes in K, but you have uncountably many conjugacy classes of settled elements. So it's going to be plenty of settled elements that are not Frobeniuses. But so this answer does not tell you one fundamental thing, or let's say 2 fundamental things. The first is, okay, but can you tell me an explicit element that is not settled? That is, sorry, a settled element that is not a Frobenius. And the second question is a little more subtle, but so these elements, do they depend on the embedding? Because when we look at this arboreal Galois representation from GK to the automorphism group of the tree, So we are labeling the nodes of the tree with the roots of the iterates of f, right? And doing this corresponds to choosing an embedding, okay? So not all embeddings, so they're gonna be conjugated. But a priori, it is possible that I show you an element that is a settled element, not non-Frobenius for a certain embedding, but if I change the embedding, then it becomes a Frobenius. So both these questions are unclear. So this is the theorem that we proved earlier this year. And so the answer is yes, we can find a lot of explicit examples that are universal. They do not depend on anything. They do not depend on F. They do not depend on the number field. They just cannot be Frobeniuses, ever. So the theorem is the following. We can find an uncountable explicit set S inside omega infinity, which has the following properties. Every element is settled. Any two elements of S are not conjugate. This is important because conjugacy maintains the same cycle structure. And if you conjugate a Frobenius, you find a Frobenius. And third, if you choose any quadratic polynomial over any number field, and you choose any embedding of its dynamical Galois group inside omega infinity, then no element of S is ever going to be a Frobenius of any prime. It doesn't matter, ramified or unramified. You don't even have to be careful about the prime dividing the discriminant of the polynomial. So these elements are just never Frobeniuses. Okay. So it's a completely universal state.
Andrea?
Yeah.
So when you change the embedding here, so I guess it corresponds to changing the labeling of the tree.
Yeah.
Do you just get like some conjugate element, or is
Probably yes. Yes.
Okay.
I think so. Yeah, you get conjugacy. Yeah. So this is the theorem. So now I want to tell you how sort of we proved it. And first of all, I have to tell you what does it mean to find an explicit example? Because so far it's not clear at all. What is an explicit element of an infinite Galois group? Usually it's very hard, right? But the nice thing is that here the picture is so practical, like so explicit, that you can actually have a notion of being explicit. And it's the following one. So elements of the automorphism group of the tree, they can be uniquely identified by something that is called their portrait. So we use this notation for the portrait. I don't know how standard it is, but I'm gonna explain it to you. So a portrait is a sequence of 2 to the n tuples of digits. So the first entry is just an element of F2. The second entry is a pair of elements of F2. The third entry is 4 elements of F2. The fourth entry is going to be 8 elements of F2, and so on and so forth.
So these are the sections of the automorphism.
Yeah.
The group theory people call it sections.
No, I'm not exactly sure they correspond to section. Probably, yeah. I have to think a bit about it. I'm not completely sure.
So you're talking about the sort of the action.
No, because I think that sections. You mean these epsilon ij are the sections? Yeah. Then yes, yeah.
Okay.
So but really, this is what is called the portrait. This is not our definition. It's called in the literature portrait. So what do these digits say? So each epsilon ij, it tells you whether the element sigma swaps the two descendants at level j plus 1 of the node that you labeled I at level j. For example, the identity doesn't do anything. So its portrait is all digits equal to 0. So you're not doing anything. 0 tells you just stay still. Don't move anything. And for example, an element swap the two halves of the tree exactly when the first digit, so the first entry of the portrait is 1. So this digit here tells you whether you should swap the two halves of the tree. So now there is a picture that hopefully makes it a little bit more clear. So suppose that you have an element whose portrait starts in this way. So you have 0, then 1, 1, then 0, 0, 1, 0. So the first 0 is here and tells you you don't swap the two halves of the tree. So alpha 1, 1 stays alpha 1, 1, does not go to alpha 2, 1. This one tells you that you have to swap these two subtrees. So all these guys, they go here and vice versa. And same thing here. And these ones and 0 tells you, so this 0 tells you here you don't do anything, here you don't do anything, here you swap these two, and here you don't do anything. And if you label the nodes here at level 3 from 1 to 8, so 1, 2, 3, 4, 5, 6, 7, 8, you will get, so your element will act as a permutation of these 8 elements. And if you read through the portrait, this gives you this permutation, 1, 3, 2, 4, 5, 7, 6, 8. You see why, right? So because, for example, say you start at 1, how do you find the image of 1? So you start from the top, and here you have a 0, so you don't go to the other half of the tree. Here you have a 1, so this means that this 1 must go here, and so 1 goes to 3. And now here you have a 0, so 3 stays still, doesn't go anywhere. So 1, 3. And same way, you can reconstruct the permutation. So to answer your question about what is an example of a settled element, a settled element, for example, odometers are settled elements, and they are elements whose portrait is the following. At every entry of the portrait, there is 1, 1, and everything else is 0. So for example, here you have 1, here you have 1, 0, here you have 1, 0, 0, 0, and below it you have 1 and then all zeros, and so on and so forth. That element is a settled element. Not only settled, but it's an odometer, so it acts transitively at all levels of the tree. So that is an explicit description of a settled element.
But
Okay.
Can you give like the polynomial or?
Sorry?
What do you mean? So you are fixing a polynomial, right?
No. Here I'm just talking about abstract elements of the automorphism group of the tree. I'm not looking at any polynomial. So here I'm just thinking of the graph. Okay. So here really it's a graph. It's just a graph.
Okay. So, but I mean, maybe the question is, does this element lie in the image of the Galois group?
It depends. Sometimes yes, sometimes no. That's not easy. That's not an easy question to answer. It can lie in the image, but it also cannot.
But can
It
we give an
depends.
example? So, but there exists explicit
Yes,
example
yes.
which line?
Yes. You can give explicit examples of polynomials such that the image is the whole automorphism group of the tree. So every element is in the Galois group. This you can do. It's not easy, but you can do it.
Thank
you. Okay. So our idea of the construction of settled element is the following. So we start with a sequence S1, S2, S3 of zeros and ones, and you construct a settled element psi of S by describing its portrait recursively. Now, I don't want to give the explicit description because it's technical and I don't want to bore you with the details. So I am just going to tell you what the cycle decomposition is at every level. Okay. So I'm just gonna tell you this. So this is not a proof for it. It's just to give you an idea of how it works. So we let Vn be the set of nodes at distance n from the root as usually, and we label them from 1 to 2 to the n. Now, suppose that your psi of S, when it acts on some level Vn, decomposes in this way. So C1 through Cr. So these C1 to Cr are disjoint cycles. And I order them by increasing length. So the first one is the shorter, and then the last one is the long. So this is just the usual decomposition into disjoint cycles as an element of the symmetric group on 2 to the n symbols. Now, you look at the next digit of the sequence. If it is a 0, Then when our element acts on the next level, it decomposes in the following way. So the number of cycles does not increase. You have again R cycles, and each of them is twice as long as in the previous level. Okay, so each of these cycles increases by twice its size. Okay, so this is to say you have an iterate of a polynomial, you have a factorization. Now all of your irreducible factors stay irreducible when you compose them with that. If the digit, oh, sorry, that's a mistake. If the digit is not 0, but it's 1, otherwise the slide wouldn't make sense, then the decomposition is slightly different. So the first cycle splits into two cycles that are as long as C1. So here you split in two. And the other cycles, they grow by twice their size, as it was happening before. So this is the only little difference. So the first cycle, instead of growing, it splits into two cycles of the same length. And so let me give you an explicit example. So suppose that your sequence is this. One, yep.
Sorry. So Andrea, so at every step, so you're only losing one cycle?
Yes.
Like,
Essentially, yes. Yes.
If you lose any, there's only one that you lose.
I mean, you grow by at most one. It's not that you lose. You're adding cycles. But you're adding at most one. Yeah.
Yeah.
Either 0 or 1. Yeah.
Mm-hmm.
So let me give you an explicit example. So suppose that you have this sequence 1, 0, 1, and then everything is 0. So V0 is just the root of the tree. So the action is trivial. So you just have a single cycle of length 1. Now you read the first digit. The first digit is a 1. So what's going to happen is that this one cycle has to split into two 1 cycles. Okay. So it will be the identity. So on V1, this element psi of S will act as the identity. Now I read the next digit. The next digit is a 0. So the identity here is the product of two 1 cycles because V1 is just 1, 2. So on V2, I split into two 2 cycles, which are 1, 2, and 3, 4 specific, if you follow the construction. Now I read the next digit. The next digit is a 1. So the first cycle, which is a 2 cycle, is going to split into two cycle. And the second 2 cycle is going to become a 4 cycle. And so if you follow the construction, you get this permutation, 1, 3, 2, 4, 5, 7, 6, 8. And from now on, you only have zeros. So these cycles, they will always grow by a factor of 2. So at all the subsequent levels, your element will decompose this way. You will have C1, C2, C3. C1 and C2 will be 2 to the n minus 2 cycles, and C3 will be a 2 to the n minus 1 cycle. Okay? So this in particular will be a strongly settled element. Okay? Not only settled, but strongly settled. In fact, you can prove easily that the element we construct this way is strongly settled if and only if you have a finite number of ones in the sequence. But this, I don't want to enter technicalities.
So you're talking about this specific example that gives you Is that because after some level everything is 0?
Yes, exactly.
Okay, so that's what I meant by losing before. So
okay.
You're constructing stable cycles, but at the level maybe you lose one cycle that is not stable.
Yes. It's very easy to see that the number of orbits is given by this very simple formula. 1 plus the sum of the digits up to level n. You see here, for example, this number is eventually 3. And in fact, you have, because you have 2 1s, and then you have to add 1. And so, in fact, you just have 3 orbits, 3 cycles. Okay, this is more or less how the construction goes. Now, I have to get a little bit more technical and tell you that when you look at the Abelianization of the automorphism group of the tree, this Abelianization is isomorphic to an infinite product of F2, the additive group, the cyclic group over the 2. And when you compose this isomorphism with the natural map that sends an element to its class in the abelianization, you get a map, which I denote this way. So this is a collection of map at every single entry, which simply does the following thing. It takes the digits of the portrait at the end, the entry of the portrait, and it sums all the digits. Okay, so I have to take an element of omega infinity and give you a sequence of zeros and ones. So I do it this way. So the first entry is simply the first digit of the portrait. The second entry is the sum of these two digits. The third entry is the sum of these four digits, and so on and so forth. Now, our theorem goes as follows. Start with any sequence of zeros and ones. First of all, psi of S is settled. And second, when you compose psi with this map from omega infinity to the abelianization, what you're doing is you're sending your sequence to this sequence. So every entry is the sum up to the entry n, and then you have to take mod 2, because here, this 0 and 1, I'm just taking them as real numbers, not elements of F2. And in particular, it follows immediately from this description that this composition is a bijection between the set of sequences and the abelianization of the automorphism group of the tree. And it follows immediately that if you take two different sequences, their images cannot be conjugate. Because if you have to conjugate elements, in the abelianization, they coincide.
So this map is actually just taking the sign n, right, for every level?
Yes, this phi n, yes, phi n.
Yeah.
So the composite, yeah, so you do this construction psi and then apply this map that sums the digits of the portrait. And what you end up is this very, very simple object, just summing and then doing mod 2. And
so that's but I mean, like, so this map, the sequence of these phi n's, isn't it just seeing it as a permutation on the nth level and looking at the sign of that permutation at every n, right? So then it's clear that they're not going to be conjugate because you're just picking different conjugates classes. Their sign is different, so they're not conjugate.
Well, I mean, it follows from the fact that it's a bijection here.
Yeah, sure.
Because, so but it follows immediately. It's a free consequence. So
okay.
So what I'm saying is all these elements that we are constructing, they're never conjugate one to each other. Okay. This for having honest examples. Okay, so this is the, say, group theoretic side of the construction. Now I have to tell you, what does this have to do with Frobeniuses? Okay, so I don't want to go too much into detail, also because my time is almost up, but I'm gonna be finished soon. So we started from this observation. It is also quite elementary. So you take a local field this time and a quadratic polynomial x squared plus c. And recall this adjusted post-critical orbit, so just the orbit of 0. With first elements, you swap the sign. Suppose that the residue characteristic is odd, so take some QP with P odd. And suppose that C has this shape, so it has negative valuation. Then when you look at the elements of the orbit of 0, you're gonna get squares. Okay, from the second term on, all you see is squares. Okay, simply because of how the valuation works in local fields. You don't really have to think much. You iterate, you put inside things that have a growing negative even valuation, and what the residue here is a square, and you can lift it by Hensel to get a square in K. Okay, so it's easy to see that every Cn is a square. So the sequence, the adjusted post-critical orbit is almost periodic. Okay, from a certain point on is constant modulo squares. And this is what we could prove. Suppose that 0 is not periodic, otherwise there is a problem. Then maybe the the adjusted post-critical orbit is not periodic, but it becomes periodic on a subsequence that is an arithmetic progression, okay? So there must be A and B such that this sequence becomes periodic in the group of K star modulo squares. With a little bit of work, you can prove. And now we sort of resorted to one old result of ours, which is the following. So it take this character phi n, which is just summing the portrait at level n. So this is one continuous character of the group omega infinity. And if you put all of these characters together, you get the map that I was showing you before towards the abelianization. On the other hand, you also have another character, very natural character of the absolute Galois group of K, which is this chi Cn, which is just the character that is attached to Cn by class field theory. So this just tells you the action on a square root of Cn. So this R is a square root of Cn, and this chi Cn is the quadratic character that is attached. And now the theorem is that, oh, sorry, this is a mistake, it is not GK, but so if you look at a dynamical Galois group inside omega infinity, these two characters, they coincide. They're exactly the same character. And this tells you that if your sequence CAN plus B is periodic modulo squares, well, then also this sequence is periodic. The sequence of the character phi with index AN plus B evaluated in sigma must be periodic. Okay. And therefore, if you have a number field and you have a Frobenius element for some prime of K, well, then you can find some arithmetic subsequence such that when you evaluate these phi characters, you get a periodic sequence. Okay. But now you can see how to prove the theorem, because now it is very easy to construct elements which have the shape psi of S, and they have the property that this sequence of characters evaluated in sigma is never periodic. Okay, for any choice of A and B. For example, stupidest example I could think of, take an element whose image is in the abelianization is done like this. It's 0, then 1, then 0, 0, then 1, 1. So you have 1, 0, 1, 1, 2 zeros, 2, 1, 3 zeros, 3, 1, 4 zeros, 4, 1. This sequence here has no subsequence that is periodic indexed by an arithmetic successor, simply because you have arbitrary long sequences of zeros and 1. So you cannot hope of getting anything periodic, because the period must be finite. But you will see arbitrary long blocks of zeros and 1. So you have no chances of finding subsequences that are periodic if the index runs through an arithmetic, some arithmetic sequence. So this is just the image in the abelianization. I promise you an explicit element, but it's very easy to recover the element. And for example, S is an element whose image in the abelianization is this 0, 1, 0, 0, 1, 1. It counts how many times you swap between 0 and 1. So you have, for example, a change, another change, then you stay the same, then you change, then you stay the same, then you change it, same, change, same. These zeros and 1, they count that essentially. Okay. So now you have constructed one element that is settled and can never be a Frobenius. And now it's easy to construct uncountably many, because, for example, you can start from this S and change infinitely many digits in the right way, or start from these elements, say, and change the first digit of each block. And therefore you get a continuous of element. It's really not interesting. You can do it in many ways. There is also some major theoretic argument that the set of sequences that have the property that no matter how you select an arithmetic sequence of indexes, you get something periodic. it should have some positive measure inside the set of all sequences. So somebody convinced of this measure theoretic argument. So you really can construct uncountably many elements. And if you add in a little bit of technicalities, you can prove it in full generality. So you can also choose any base point. So I didn't talk about base points, but essentially it's you play the same game, but instead of looking at f equals 0, you look at f equals alpha, f squared equals alpha, and so on and so forth. So you get little different Galois groups, but the ideas are the same. So here you have to be a little bit more careful in constructing these settled elements, but nevertheless you can do it. So you can construct really an uncountable set of settled elements such that no matter how you choose your polynomial, your number field, nothing your prime, they can never be Frobeniuses. And this is as explicit as we could get it. Okay, thank you. I'm done with this.
Thank you, Andrea.
Thank you very much.
Are there any questions?
I have many questions. Can I start?
Of course, yes.
So first of all, does this fact give any information about the result, give any information about C? I mean, it seems to me that it's very combinatorial in some sense.
Any result about what? Sorry.
So the constant C you had, so you have like x squared plus C. So does it give anything about C? That the fact that I mean, I'm saying that this consideration that you have something is settled or not. So
I don't know about
C is
that.
irrelevant. So.
Yeah. So the consequence that you automatically get is that certain factorization patterns do not happen ever. So the factorization patterns that are sort of described by these bad elements are settled, but they never happen. There are no polynomial which follows that factorization pattern, which is, let's say, not easy to prove otherwise.
Okay, maybe I ask another question and then like two questions. I mean, I want to know.
Of course.
First of all, if the degree of the polynomial is not 2, can we say similar things? Just everything like generalizes, or
so the construction of settled elements for sure generalizes. Nothing really changes. The problem is this theorem here. So here we don't know what character you should take instead of this chi ci. What you can do is you can generalize it to so-called unicritical polynomials that are of the form x to the n plus c. Instead of being x squared plus c, you get x to the n plus c. And this is a very specific. The point is that in degree 2, there is no loss of generality in looking at polynomials of the form x squared plus c, because you can always get rid of the linear term without touching anything. In higher degrees, you can repeat everything I said for polynomials of the form x to the n plus c. But if you take a generic polynomial of degree n, then this result is really, we really don't know what to have here instead of this chi ci. It's even for, say, cubic polynomials, we don't really know. So
like for cyclotomic polynomials, is it like very hard, or
I don't see why cyclotomic polynomials should be any different than from generic polynomials. Because when you iterate cyclotomic polynomials, you don't get cyclotomic polynomials.
I mean, I want to know what is the relevance for number theories. Of course, these are, I mean, theory.
Truly, the motivation is understanding the factorization pattern of the iterates. So, or let's say more in general, I mean, what's really interesting to me beyond the factorization of the iterates, which is a very legitimate question anyway, is to understand what are the Frobenius elements in these large Galois groups. So this is really the heart of the matter. Because when you have finite extensions of number field, you have Chebotarev. So there is no description of Frobenius elements. Every element is a Frobenius. Here, it's not like that. And it's definitely not clear which elements should allow to be Frobenius. So this is really the concrete motivation, if you want, for studying all this.
The for finite groups that we get out of this are very particular, right? Like for saying like there are two groups or something like this.
Yes, there are proto groups. Yes, absolutely.
So I cannot just try to like put into this. I have like a for finite group, like Galois group, and then think about it as a how do you say like this automorphism of the tree like this, right?
Yeah, but
I mean, these are very particular kind of Galois groups that you get from this construction.
Sure, absolutely. Yeah. But the problem is that it's very difficult to relate the tree, if you want, the properties of automorphisms of the tree to arithmetic properties of the polynomial you started with. This is the delicate part. So being able to link the two things. This theorem here is an example. So this gives you a very strong link between something that comes from the combinatorics of the automorphism group of the tree and something that comes from the arithmetic of the polynomial. Okay, because these CIs, they just depend on the polynomial. They're just the orbit of zero. And so this object here on the left depends only on the polynomial, and this object on the right, and this object on the left depends on the combinatorics of the tree. So this is the type of theorem you want to look for, but I mean, there are not that many, let's say.
And this is very hard, right? Is this?
Yeah, it is. No. This what is very hard.
No. Okay.
I mean, many things are very hard in this area.
Okay. Can I ask one more question? Or I mean, I'm taking time. Can one give an explicit example of a Frobenius which is theta? Is this easy?
Yes. This you can do because you can simply take a stable polynomial. So you take a polynomial that is stable modulo p. So for example, x squared with x squared plus 1, you can do it because x squared plus 1 is stable modulo 3. So for sure there its Frobenius is gonna be an odometer. And I'm pretty sure you can describe it explicitly. Yeah, so this you can do.
Thank you.
Okay, are there any other questions? So Andrea, when do you see the paper?
Yeah, the paper is finished. It's just we need to just read it one last time. Both me and Carlo were a bit busy with. I am very busy with preparing courses for next semester, and he's busy with other stuff, and so we didn't get a chance. But it's finished. I mean, just need a last revision.
Okay, so soon.
So hopefully very soon.
Can I ask one question?
Of course.
So these arboreal Galois representations, is there some sort of Lagrange correspondence kind of thing for them?
I wouldn't go that far as into Lagrange correspondence. There is a conjecture which is the analog of Serre's open image theorem, because these objects are in a way, you can see them as just wild generalizations of Galois representations on Tate modules of abelian varieties. In fact, if you think for a moment, the Galois representation on a Tate module of an elliptic curve, let's say, is exactly this construction. Where it's a little different, of course, because as the root of the tree, you will put the zero element of the group structure. And then at every element, you put the p to the n torsion, p to the n torsion of the elliptic curve, right? And then you get exactly the same picture. But the difference there is that since you have the group structure, you have a lot more structure. So it's true that the image lives inside the Galois group of the tree, the autoreflex group of the tree, but it's much, much smaller because of all the symmetries that come from the group theory of the curve. So in a way, this is a wide generalization. There is a conjecture that is exactly the analog of Serre's open image. So it tells you when the image of this map has finite index inside here.
I see.
But we are very far from it. There are partial results, but they rely on ABC. So it's a tough question. So Langlands correspondence, I haven't heard anyone even daring to formulate an analog.
Thank you. Yeah.
Sure.
Maybe I'll ask something and then we can finish.
Of course.
So I don't remember what you called it. So these maps to F2, so for each end, you have these summing up these epsilon I.
Exactly.
So I think it's what I call the sign map, but then it looks much easier to me to think that way. Does that help? Like get any?
No. So the fact is that we introduced this notation for another because we didn't know of the sign map. So we came out with this notation on our own, and for us the additive notation was easier to use. So this is why we use additive F2 and not C2 with the sign map, but it's exactly the same thing. Yes.
Yeah. Okay. So writing it like this doesn't add anything extra.
No. I mean, it's just easier notation wise for us. I don't know. We like to think additively. So.
Okay. Thank you. All right. Let's thank Andrea again.
Thank you.
So maybe I can ask something. I mean, so these are